Hi everyone. In the last lecture, we have discussed about linear operators between two Hilbert spaces. Today, we will be discussing about maps between two Hilbert spaces which are bounded. So let us start with basics of bounded maps. Before that, let us look at what is a bounded set in the setting of Hilbert spaces. So let us take H to be Hilbert space. So for r bigger than 0, B0R denotes the set of all x in H such that norm of x is less than r. Here the norm is nothing but the norm which is induced from the inner product of H. So norm of x is inner product of x with itself and square root. So this is the, so all the time we will be looking at norms which are induced from the corresponding inner products of the Hilbert space. Okay, so this is called open ball centered at 0 with radius r. B of 0 r closure is set of all x in H such that norm x less than or equal to r. This is the closed ball r discs centered at 0. Similarly, we denote ball centered at a point x in H by B of xr is set of all y in x such that norm of y minus x is strictly less than r. This is nothing but we can actually show that this is x plus ball centered at 0 with radius r, and this is nothing but x plus r times ball centered at 0 with radius 1. Okay. Similarly, we can define what is B of xr closure. This is exactly set of all y in x such that norm of y minus x is less than or equal to r. So this is the closed ball. This is the closed ball centered at x with radius r. This is the closed ball, the other one is the closed ball, sorry, the open ball centered at x with radius r. Okay, so in this case also we can write this as x plus r times ball centered at 0 with radius 1 and closure of this one. Okay, let us define what a bounded set is. So a set or a subset B of H is called bounded if there exists some m positive such that norm x is less than or equal to m for every x in H. Okay, so in other words, we can say that the set B is completely inside the ball centered at with 0 and radius m. In fact, here it is closure because we are saying norm x less than or equal to. So if you are able to cover the given set with a closed ball centered at 0 with radius m, then we say that the original set to be bounded. Now we are interested in looking at maps which takes bounded sets of domain into bounded sets of codomain. Such maps we call as bounded maps. Definition: let T be a linear map from H1 into H2, where H1 and H2 are complex Hilbert spaces. Then T is said to be bounded if T of B is bounded in H2 for all bounded sets B of H1. That means whenever B is bounded in H1, T of B should be bounded in H2. So let us try to look at what is the meaning of this. So B is bounded implies there exists some m bigger than or equal to 0 such that norm of x with respect to the first Hilbert the norm of the first Hilbert space is less than or equal to m for every x in B. Now T of B is bounded means is bounded implies that there exists some number k positive such that norm of T of x, because every element of TB is of the form T of x where x is coming from B. So this is with respect to the second Hilbert space should be less than or equal to k times for every x in B. Okay. So whenever norm x less than or equal to m, then norm of Tx should be less than or equal to say k for some quantity, positive quantity k. So now let us take, so if x is in H1 with x1 non-zero, then we can say that x by norm x is in the is on the unit sphere of the first Hilbert space. So we can say that this implies, then we can say that x by norm x and multiplied by m is in the closed ball centered at 0 with radius m, because norm of this element is less than or equal to m. Okay, so whenever norm of an element is less than or equal to m, so its image norm is less than or equal to k. So let us use that fact. So then this implies norm of T xm by norm x1 is less than or equal to k. So this implies that norm of Tx is less than or equal to k by m multiplied by norm x, and this is for any x in H1 with norm non-zero. So this implies norm of Tx is less than or equal to k times norm x for every x in H1 and x non-zero, k by m. And when x is 0, automatically left hand side is 0 because T of 0 is 0. Anyway, norm x is on the right hand side, it is 0. So that means this inequality is true whenever x is 0. So from this we can conclude that. So the conclusion is the following. T is bounded implies that there exists some constant. So k by m we can call as some L such that norm of Tx is less than L times norm x for every x in H1. So the conclusion is that whenever T is a bounded linear map, that means T maps bounded sets of H1 into bounded states of H2, then we were able to find a constant L which is strictly bigger than 0, such that norm Tx less than or equal to L times norm x. Now a question we can ask is that, is the converse true? Question, is the converse true? That means we want to show that if there exists a L satisfying this condition, can we say that T is bounded? Suppose there exists some, let us say, L bigger than 0, such that norm Tx is less than L times norm x for every x in H1. Can we say that T is a bounded linear map? Okay, so let us start with a bounded set. Let B be a bounded set. Then there exists, so we want to show that T of B is bounded. So then because B is bounded, there exists M such that norm of x is less than or equal to M. Okay, now if you look at image of x under T, means you can have norm Tx by the above condition. This is L times less than or equal to L times norm of x, but we know that this is less than or equal to M times norm x, M. Okay, so this implies that T of B is bounded. So here L into M is a positive number. We can say that T of B is bounded. So the conclusion is the following, that whenever T is a bounded linear map, then we can say that there exists a constant L such that norm Tx less than or equal to L times norm x. So this is a characterization of bounded linear map. In fact, we can show that this boundedness property is equivalent to the continuity of the linear map. So here we state that as a theorem. So let us take T to be a linear map from H1 into H2. Then the following are equivalent. The first condition is T is bounded. Second one, that there exists some number L bigger than 0 such that norm Tx is less than L times norm x for every x in H1. Okay. The third is T is continuous on H1. Fourth one is T is continuous at a point 0. Equivalently, you can say that there exists some k positive quantity such that norm of Tx minus Ty less than k times norm x minus y. This is 2, and this is for every xy in H1. So these conditions are equivalent. So there is an importance for this result. It says that boundedness is equivalent to continuity of a linear map. on the Hilbert space H1. And since T is linear, from that we can also say that it is enough to look at continuity at a single point, namely 0. So that is given by condition 4. So this is the advantage of having a linear map, and that means whenever T is continuous at a point 0, then T is continuous at every point. Okay, so let us look at the proof. So we have already shown that 1 is equivalent to 2. Shown that 1 is if and only 2. Now we want to show that T is continuous on H1 by assuming the condition 2. So 2 implies 3. Assume 2 holds. Okay, we want to show that T is continuous on H1. So for that, let us take, so let X be an arbitrary point of H1. We want to show that T is continuous at X. That means if Xn is a sequence converging to X, we want to show that Txn is converging sequence to Tx. So let us take Xn is a sequence from H1 such that Xn converges to X. Okay, so now we want to show that, so by condition 2, so by the hypothesis, norm of T of Xn minus X is less than or equal to L times norm of Xn minus X, right, by 2. So this implies this is nothing but norm of Txn minus Tx is L times norm of Xn minus X. This is in 1 now. Okay, we know that Xn converges to X, so this converges to 0 as n tends to infinity. So this says that Txn converges to Tx as n tends to infinity. So this, from this we can conclude that T is continuous at X in H1. Now X is an arbitrary element of H1. So as X is arbitrary, so we can conclude that T is continuous on all of H1. Okay, so we have shown that 2 implies 3. Now 3 implies 4 is trivial because T is continuous at every point, hence T is continuous in particular at the point 0. So 3 implies 4 is trivial. Now we want to show that 4 implies 5. That means we have to assume that T is continuous at 0 and show that T satisfies this condition. So this condition is known as the Lipschitz condition. If there exists a case satisfying this property, we say that K is the Lipschitz constant, and this condition is known as the Lipschitz condition. Okay, so assume that T is continuous at 0, and we want to show that T is Lipschitz. T satisfies the Lipschitz condition. Okay. Okay, so let us since T is continuous at 0 for epsilon positive, there exists delta bigger than 0 such that whenever norm x is less than delta implies norm tx is less than epsilon. So this is by definition of continuity at 0. Let us take x and y in h1 with x minus y non-zero, or we can say that x is not equal to y. Then we can say that x minus y by norm x minus y. So this is an element of the unit sphere of h1. That means norm of this element is 1. So if you multiply this with delta, this is in the ball centered at 0 with radius delta, but if I multiply with delta by 2, so norm of this whole element is less than delta by 2. Okay, so norm of this is less than delta by 2, that is strictly less than delta. Now we know that whenever norm x is less than delta, then corresponding norm of the image is less than epsilon. So for this element, so let me call this is star. So by star we can say that, so norm of this whole element x minus y by norm of x minus y1 delta by 2 is less than epsilon. So this implies that norm of tx minus ty, because t is additive, this is less than or equal to epsilon times norm x minus y, and this is divided by delta. Okay, so this implies norm of tx minus ty is less than or equal to k times norm x minus y, where k is nothing but epsilon by delta. Since epsilon is fixed and delta is also fixed, this is a positive quantity, and this epsilon and delta, this k does not depend on x and y, because we assume that t is continuous at 0. Because of that, given any epsilon, we got this delta with this property, and whenever x and y are two distinct elements, we derive this inequality. So we can say this is less than also. So the ellipsis condition is satisfied. So we can conclude that 4 implies 5. Now 5, instead of showing 5 implies 1, we show that 5 implies 2, because 1 and 2 are equivalent. So taking y equal to, so we want to show that 5 implies 2. So take y equal to 0 in the ellipsis condition, that is, let me say this is 1. In 1 to get 2. So from this we can conclude that 5 implies 2. So we have shown that 1 if and only if 2, and 2 implies 3, 3 implies 4, and 4 implies 5, and 5 implies 2. Then the cycle is complete. You can say that all these conditions are equivalent. Okay. So let us fix a notation for set of all boundary linear maps. So as we have just now proved that boundary linear maps are nothing but continuous maps, or continuous maps at particular point. We can say it is enough to verify continuity at one point instead of verifying that continuity at every point. So let us look at a notation. So we say, we denote set of all boundary linear maps from h1 into h2 by b of h1 h2. So this is nothing but set of all linear maps L of h1 h2 such that T is bounded, or we can say that T is also continuous. And if h1 equal to h2 equal to h, then we write this B of h1 h2 by B of h for notational simplicity. Okay. Now the question we can again ask is B of h1 h2 non-zero whenever h1 is non-zero and h2 non-zero. Can we get a non-trivial bounded linear map from h1 into h2 whenever h1 and h2 are non-zero? The same example that we have given earlier, that will work. So let us take x in h1 and y in h2. Both are non-zero. Let us take two fixed elements. So define T from h1 into h2 by T of z equal to inner product of z with x multiplied by y. So this inner product is in h1 and y is an element of h2. On the whole, this scalar multiple of element of h2, hence its value is in h2. Z is in h1. We can easily check that T is linear, and to show that T is bounded, so it is enough to find a constant k satisfying the condition that we have seen earlier. So consider norm of Tz. This is nothing but norm of z, inner product z with x multiplied by y. So this is a scalar. So this is mod inner product z with x multiplied by norm y. This is into by Cauchy square inequality. You can say that this is norm of z in Hilbert space h1, norm of x multiplied by norm of y2. So we can say that T is bounded and norm of T. So we have okay. So we can only say that norm of Tz is less than or equal to k times norm x1 multiplied by norm y2. Okay. So sorry, this is nothing but this is k times norm z for every z in h1, and here k is nothing but norm of x multiplied by norm of y. This is equal to 0. You can say that this is a bounded linear map. That means we can conclude that B of h1 h2 is non-zero whenever h1 and h2 are non-zero. Okay. So let us again look at bounded linear maps. Let us take TVA bounded linear map from h1 into h2. That means then there exists some k bigger than 0 such that norm of Tx is less than k times norm x for every x in h1. Okay, now let us take x to be non-zero. So let us take x non-zero. Then actually norm of x is non-zero. We can divide this inequality by norm x both sides. Then we can get norm of This is less than or equal to k. So left hand side depends on the vectors x, whereas right hand side is a fixed quantity. So this is finite. So we can take even the supremum of norm tx by norm x. This is less than or equal to k. Okay. The left hand side quantity we call as a norm of the operator. So it is defined by norm of t as the supremum of norm of tx by norm x. X is in h1, x non-zero. Whenever x is 0, t of 0 is 0, and that quantity is anyway strictly less than the supremum. So when t is bounded, this quantity supremum of norm tx by x is finite. So that we call as a norm of the operator. So this is norm of t, or it is also known as the operator. Okay. So whenever t is a bounded linear operator, we can conclude that norm of t is a finite quantity. There are different ways of calculating norm of an operator, so that we will be proving in the next class. Thank you.